dot, right? So we're talking about vectors and dot products. Here's the definition for the dot product for vectors u and v. So u has horizontal and vertical component u sub 1, u sub 2. V has horizontal and vertical component v sub 1, v sub 2. So they're just like two different vectors. And then here's your dot product. U dot v is equal to u sub 1 times v sub 1 plus u sub 2 times v sub 2. So what you're doing is you're multiplying the horizontal components, you're multiplying the vertical components, and then you're adding those two products. Which means if you think about that with vectors, your answer is just a single number. So the answer to a dot product is a scalar. And we use the dot product for a few different things here, and you'll see those on the next slide. But it's not another vector. Like when you added the vectors, like we just did on that homework assignment, when we added the horizontal components, we added the vertical components, and we got a new horizontal and vertical component. So it was still a vector. This is not a vector. We'll do one example real quick where we calculate a dot product. It's going to go by fast. It's not hard. We're going to find the dot product for u and v. And I wanted to write these in linear combination form just to kind of help us, I can present a vector to you in either linear combination or component form, and you should be able to pick out your v sub 1, v sub 2, your horizontal component, your vertical component. So u is negative 6i minus 3j, v is negative 8i plus 4j. Just for the sake of notes and learning how to do something, I'm going to go ahead and label. If this is my u vector, negative 6 is u sub 1, negative 3 is u sub 2. And then negative 8 is v sub 1, and positive 4 is v sub 2. Right? But most of us probably don't have to label those things. We want to do the dot product, u dot v. So I'm going to multiply my horizontal components, u sub 1, v sub 1. That's going to be negative 6 times negative 8. Add it with the product of my vertical components, negative 3 times 4. And what does that give me? 48 minus 12. So 36. Notice, it's not a vector. It's a scalar. So it's just a number. Kind of reminds me back in chapter 8 in first semester when we did matrices, and matrix had a determinant. It was just like a number that went with the matrix, but it wasn't another matrix.
What is it though?
So we can use it for some different things. To answer your question, I can look at that up like a good visual for you, but I don't have that right now. So I don't want to say too much. But you'll see that we can use the dot product, just like we use the determinant for different things, we can use the dot product to find some other things about our vectors. This don't write down. If you want to make a note in your notebook about properties of dot product, you can say that they're on page 431. There are a couple of questions that will say something like use the properties of dot products, so then just flip back to that page and you can see them. Overall, if you kind of look at these, they're going to make intuitive sense to you. A u dot v is going to end up being the same thing as v dot u. Okay, because you're going to be multiplying the same things and adding the same things. If you took a 0 vector, which would be 0, 0 for horizontal and vertical component, multiply it by another vector, your dot product is 0. This is an example where if you add two vectors and you do a dot product with some other vector, that's like doing two dot products and adding them up. This one is the one, I think there's a couple questions on your homework, so I'm just going to talk about this one. Notice it says v dot v. So that means you're taking a dot product of a vector with itself. Okay, so I'm going to just show you kind of algebraically what that means. Suppose v is the vector v sub 1, v sub 2. If I did v dot v, I would take horizontal component times horizontal component, so v sub 1 times v sub 1, plus vertical component times vertical component, v sub 2, v sub 2. And those can really be written as v sub 1 squared plus v sub 2 squared. And then this sort of makes me think about something that we've seen before. The magnitude of v is the square root of v sub 1 squared plus v sub 2 squared. So they're saying this is not the magnitude, but it is the magnitude squared. If I just square the magnitude, it will give me v sub 1 squared plus v sub 2 squared. So v dot v is the magnitude squared. Now in the homework, I think they'll ask you to use the properties of dot products to do the magnitude. So you could do the dot product and then square root it. You have your magnitude. That is the same thing as regular magnitude. So just something to think about. Nothing to stress about. Okay, here's a formula you want to put in your notebook. And as you're writing it down, I'm going to remind you. This formula will be provided on the quiz on Friday. This formula will be provided on your test next Friday. All other formulas related to vectors are your responsibility. So that would include magnitudes, direction angles, component forms, linear combination, this formula is for the angle between two vectors, which is different than the direction angle. The direction angle is a single vector related to the positive x-axis. So just like an angle in standard position from chapter 4. So think about as you're going to be responsible for seeing this and knowing what to do, what is happening in this formula? Well, in the numerator you need a dot product of two vectors. So you'll calculate that. That's easy. That's a number. Okay. And then here you're going to do the product of the magnitudes. So you just do a magnitude of one, magnitude of the other. What's their product? When I do this problem, finding the angle between two vectors, I don't simplify the radicals. Because why? I'm going to be doing inverse cosine at the end. So I don't need them to be 2 square root 5. I'll just leave it square root 20. Okay. And notice, to solve for theta, you'll have to inverse cosine. So again, it's not a direction angle like positive x-axis. Here's my vector out in the world. Quadrants 1, 2, 3, or 4. It's here's a vector, here's a vector. What's the angle in between? Here's a vector, here's a vector. What's the angle in between? This always calculates our smallest angle. Okay, so I'm going to draw a picture of two vectors. Vector, vector. Because you're doing inverse cosine, and inverse cosine is that half moon for quadrants 1 and quadrant 2. It answers from 0 to 180. You'll always get a smaller angle that's between 0 and 180. Can include 0 and 180. But it will never give you, there's really infinitely many angles between these two. It won't give you the larger one, And you could also think about like coterminals, adding one. But it'll give you the smallest angle between the two. And then the other thing to note is that if the angle is 0 or 180, the vectors will be parallel. If it's 0, they're going in the same direction. If it's 180, they're going in opposite directions. So we're going to use this formula to also, we're going to calculate an angle, actually, I think. These are the same two vectors that I gave you before, right? So we already know the dot product. What's the dot product? U dot V was 36. Okay, great. Okay, find the angle between those two vectors. Well, we're going to set it up. Cosine theta equals the dot product divided by, and now we need the product of the magnitudes. Well, magnitude should be a pretty easy calculation for you at this point, right? Just square both components. 36 plus 9 is 45. And 64 plus 16 is 80. Now, if you're going to type it into the calculator like this, you need a big set of parentheses around your denominator. Or properties of radical says a square root of 45 times the square root of 80 is really a square root of 45 times 80. So I could just do one radical and then I don't need parentheses. See if you can type this in, and you have to inverse cosine. See if you can get the same angle as me.
What do we round to?
I'd say for the angle, like the nearest tenth is fine. I'm not too particular on this one. I think I get, is it 53.1?
Yeah.
53.1 degrees. So see if you can get that number. If you're having trouble, show your neighbors, show me. Let us diagnose what your issue may be. Okay, everybody's probably going to need to be in working order.
Oh.
You might be missing a parenthesis or something like that. Check your mode. Are you in degree mode or radian mode? Do you do inverse cosine?
Well, you can do it after. You don't have to. Like, you can copy and paste.
Now, one thing I like to do sometimes, is just check, does that make sense? Where would the vector -6, -3, 1, or -3 be? In quadrant 3. So I'm going to say there's my vector. Where would the vector -8, 4 be? In quadrant 2. Does it look like the angle between them could be 53.1? Yeah. So it seems like a reasonable answer to me.
I know I did wrong on that one. I texted.
Oh, yeah. You got that point. Oh, wait,
Yeah.
that shouldn't matter.
Really?
And don't you have to, like, hit the arrow? and
You
use
don't
it?
want to close, you don't want that. Oh, wait. Okay, the cosine, you don't want to close the
close it right away.
parenthesis on 36. Because then it's going to do the cosine of 36, which you can't do. Anybody else having trouble? Okay.
I wish you would just scan.
Oh, yeah, that's cool.
That'd be nice.
That would be nice.
There's
That's,
your $1 million
hey,
idea.
yeah, there is $1 million idea, Kenzie.
I got it right.
You have to
Try.
inverse cosine that. That's the cosine of theta equals 0.6. You're right. Did you get it, Tom?
Yep.
Yes or no?
Yeah.
Okay. Okay, so 2 more things we got to talk about real quickly. First, orthogonal vectors. Orthogonal is a fancy way to say perpendicular. What does perpendicular mean? Intersect at a 90-degree angle, right? Okay, 90-degree angle. So we just did a formula. Cosine theta equals u dot v over the magnitude of u times the magnitude of v. And we said that would get us the angle between two vectors. And we're saying in the end, the angle is 90. What is the cosine of a 90 degree? 0. So the step before that would have been cosine theta equals 0. What's the only way this fraction equals 0? If the 0 is where?
On the top.
In the numerator. The only way that's true is if u dot v equals 0. So, shortcut, two vectors are orthogonal if and only if dot product is 0. It's like a shortcut. If I ask you to say whether or not two vectors are orthogonal and you do the full formula and find out it's 90 degrees, same answer. Or it's not 90 degrees. Same answer, yes or no, they're orthogonal, but way more work. If you realize at the moment you do the dot product, if the dot product is 0, the answer is yes, because the cosine of 0 is 90 degrees. Or sorry, the cosine of 90 is 0. Or if you realize it's not 0, there's no way it's going to be a 90-degree angle, then you can say no. You don't have to keep going in the formula. So if I were asked if these two vectors were orthogonal, I would only calculate dot product. U dot v equals 6 times negative 1/3 plus 10 times 1/5. That's negative 2 plus 2, which is 0. So yes, they are orthogonal. If I say no, or if I get any other number, I say no, they're not orthogonal. Okay. Does that make sense? Okay. So just like a little shortcut for you. Last thing we want to talk about is work. How many people were in physics? A nice little handful in here. Okay, excellent. So this formula should sound familiar to my physics people, although maybe slightly changed. You guys maybe use letters. When you do work, does it matter if it's capital or lowercase w? Do you have to talk about that? Okay. Do you remember force was? I feel like force is usually capital.
Yeah, force for sure is.
And then V was lowercase.
Looks right to me.
Physics, I think you guys use a different word than distance. Instead of distance, you call it displacement. But those two things mean the same. Like, where did I move to,
I
right?
think it's like theta or triangle x.
Oh, yeah.
Like that's what.
Change it.
Yeah.
Yeah. Displacement is a change in location or a change in position. Yeah, sure. It's all the same, right? It's just like what class you're in. Doesn't matter. So work is force times distance, but the thing that you'll have to remember is that force, you don't want the total force being acted on the object because you only want the force required to move the object in that particular direction. Okay. Sometimes they refer to that as projection. So like if I were to take my teacher desk and rearrange my room, I'm going to push it. It's really heavy. If I was going to like push my desk over so that I would have a new location, I'm pushing, like imagine yourself pushing your desk. You're pushing down and forward, right, to make that happen. But if I'm trying to calculate the work that it would take for me to move my desk to the back of the room, I don't want to count my force of pushing down. I only want my horizontal component of me pushing it forward. Okay, so that's where we're going to choose the magnitude times cosine or the magnitude times sine. I'll say most of the time we're working with pulling and pushing. So we're doing horizontals. So you're going to do a lot of magnitude times cosine. But certainly we could, think about moving something up or down like on a pulley system. And then we would talk about a vertical. Okay. So the component force that we want is what we talked about yesterday. Why we did. What's the vertical component of velocity? What's the horizontal component of velocity? So here's my last example, and it's page 439, number 84. And if in case you don't want to write it all down, okay, you can always go back and refer to it. I've got a ski patroller pulling a rescue toboggan. Person's all wrapped up, but
Rescue toboggan.
they're okay. I don't know. Maybe it's supplies. Maybe it's not a person.
That does not look like a person.
It doesn't look like a person?
Actually,
I don't
it
know.
does. It looks kind of weird.
I don't know what it is. It's supplies.
Their legs are
Everybody's
very,
fine,
Their legs
okay?
are very, very short.
Okay, the ski patroller pulls a rescue toboggan across a flat. I don't know what a rescue toboggan really does. Across a flat snow surface by exerting a force of 35 pounds on the handle. So just like yesterday, we were doing like some with the initial velocity. That was the magnitude. Like that was all of the velocity of the object. All of the force of our object is our magnitude. So that's 35 pounds on the handle. And that's him, like think about if you were going to be pulling something, you're pulling like forward horizontally as you move, but you're also pulling, you have some upward pull as well. Okay. The angle that it makes is 22 degrees with the horizontal. Find the work done in pulling the toboggan 200 feet. Okay, horizontally. So we're going to do work equals our horizontal component of force times distance. Our horizontal component of force is going to be magnitude times cosine. So that would be 35 times cosine 22. Maybe I'll write magnitude times cosine theta right up there. And then what's the distance? 200 feet. You get a big number, so don't be alarmed. Is it
6,490.29.
So 6,490.3, and then and some people in third hour said in physics you would call that joules.
Yeah.
Okay, mathematicians, different breed of people, and they're just gonna say, what was your label for force? Pounds. What was your label for distance? Feet. So we just call it foot pounds.
Because it wouldn't be a joule because it's not in the right units.
Okay, good. So that's why we don't mess around. Would you have to convert it?
Yeah.
Yeah, so we don't do that. We're mathematicians. We're doing something. We're just kind of like, nope. So we're just call it foot pounds. If you call it pounds feet, I'm not real too.
Because a joule's
like,
like
particular.
Newton per meter.
Yeah, oh, okay, so you'd have to make the conversion. Okay, I thought this period was longer, so I thought we would have more time to work on our homework assignment. My apologies. Okay, but you do have a homework assignment. Hopefully your vector work isn't taking you too long at night. Is that true? It's taking you a long time?
It actually is.
Oh no.
It's a lot.